So we are continuing on with inverse functions. In the last video, we figured out how to find the inverse function. And so let's go ahead and do that on our next example. First, we want to prove that our function is one-to-one. Second, if it is one-to-one, find the formula for the inverse. And third, graph that function to double check that it is in fact folded over the line y equals x and that we have that inverse for that function. At this time, I suggest that you pause the video and see if you can do these 3 steps all on your own. Okay, so to prove that our function is one-to-one, we can either graph it by hand or by calculator, or we can do it by proving the formal definition that we saw in one of the previous videos. I'm going to go ahead and do the formal definition. It says if f of a is equal to f of b, then a has to be equal to b. So plugging a into my function and plugging b into my function, I can see that my 2's cancel out. I can take the cube root of both sides with no repercussions. Remember, if you take an even root, then you have to insert a plus or minus, and so that would change the outcome of this. But cube roots, no big deal. And so that tells me that a is equal to b. So that proves that this function is 1-to-1. All right, now we actually want to find the inverse. So I have y is equal to x cubed plus 2. Interchange my x and y. So x is equal to y cubed plus 2. And now solve for y. So I need to subtract 2 from both sides. So it gives me x minus 2 is equal to y cubed. To get rid of the cube, I need to cube root it. And so that tells me that y is equal to the cube root of x minus 2. Or if I want to put this in official notation, my inverse function is equal to the cube root of x minus 2. So I have my original function, f of x, and I have my inverse function, f inverse of x. Now, if I want to graph this to confirm that they are in fact inverses of each other, I can graph them by hand, but I think it's a little easier to go ahead and utilize my graphing calculator. So that's what I'm going to do. So in my y equals, let me insert my original function, x cubed plus 2. And in my y2, let me insert my inverse function. And so the cube root is underneath this math button here, so math. And we see option 4 is the cube root. So I'm going to select option 4, and then I type in my x minus 2. I'm going to leave my y equals x in there because I know that's the line that I'm trying to reflect over. So let me go ahead and graph this on the squared window, zoom 5, of which I have last time. So my blue line is my original equation. My red line is my inverse function. And if I were to fold this over my y equals x, of course they match up, so that means we did in fact find the correct inverse. So that finishes up example 2, and let's go ahead and move on and do this with one more, example 3. So consider f of x to be 3 minus x over x plus 4, the same instructions as the last 2 examples. I suggest that you pause the video and work this one on your own. So in part A, to determine if this one is one-to-one or not, again, we can graph it, or we can do our formal definition. That's what I'm going to go ahead and do here. F of A is equal to F of B is going to tell me that A has to be equal to B. So 3 minus A over A plus 4 is equal to 3 minus B over B plus 4. When I have one fraction is equal to one fraction, the easiest way to go about it is to cross multiply, or we can do that fraction magic trick and multiply by the least common denominator on both sides. On the left, I have 3 minus A times B plus 4. On the right, I have A plus 4 times 3 minus b. So let's FOIL these out. 3b plus 12 minus ab minus 4a is hopefully equivalent to 3a minus ab plus 12 minus 4b. So now I need to show that these are equivalent. Well, let's do the easiest things. If I subtract 12 from both sides, that eliminates the 12 from both sides. If I add an AB to both sides, that would cancel out my AB from both sides. So at this point, I have an A and a B on opposite sides. Let's move them to be on the same side. So let me move my A's to the left, and let me move my B's to the right. So to move my A's to the left, I subtract 3A from both sides, gives me negative 7A. To move my B's to the right, I subtract 3B from both sides, and that gives me negative 7B. Of course, if I divide both of these by negative 7, that cancels out, and that proves to me that A is equal to B. So that proves to me that I have a 1, 2, 1 function. So part A is done. Okay, now I'm on to step B. I want to show that if this function is 1-to-1, which it is, then we need to find a formula for its inverse. So let me get rid of all of this here and do my 1-to-1 steps. So first I have y is equal to 3 minus x over x plus 4. Interchange my x and y's. Now I need to do that for all variables. So I need to put a y where both of these x variables are. So this gives me x is equal to 3 minus y over y plus 4. And now I need to isolate my y variable. Well, let me first get rid of the fraction format, so I can either put this over 1 and think about cross multiplication again, or I can think about that magic trick with my fractions again. Either one works. So I have x times y plus 4 is equal to 3 minus y times 1. Distribute my x over here. Xy plus 4x is equal to 3 minus y. Put my y's on the same side because that's what I'm trying to do is solve. So let me move that to the left by adding y. And let me move my 4x to the opposite side by subtracting 4x. So lots of arrows going on here. On the left, I have xy plus y. On the right, I have 3 minus 4x. Now, I'm trying to isolate y, so this is the most difficult step for students to see. But notice since I have y and both of these terms over here, the way to get them into one y is to factor them out. So I take out a common factor of y, and that leaves me with x plus 1. Then if I divide by x plus 1, that leaves me with my y isolated, which is what I wanted to do. So my inverse function, f inverse of x, is equal to 3 minus 4x over x plus 1. So I have, in fact, found the inverse. Okay, let's go ahead and graph this to double check, but I'm going to warn you that there's going to be lots of things going on, and without colors, this is probably going to be really difficult to visualize. But mine's a little bit easier because we have those colors on here. If we wanted to talk about graphing this by hand, I think this is an excellent review section. If I look at this, I know that when my denominator equals 0, I have a vertical asymptote there. So I have a vertical asymptote at -4. And now considering the horizontal asymptote, we know that we find that by looking at the leading degrees. So I look at these here. I see that they're equivalent. And so I have the middle face case. So I look at my coefficients. I have a -1 over 1. So I have a horizontal asymptote at -1. So that's this here. Then I could do more work to figure out where my intercepts are and where my graph actually falls. But this gives you a good indication of what the graph should look like. Remember that it's going to have horizontal and vertical asymptotes, but the graphing calculator is not going to graph for you. And we need to be doing the same thing with my inverse function. So let me do that here. If I figure out where my denominator is equal to 0, I see that's at -1, so that gives me a vertical asymptote at -1. And if I look at my leading coefficients for my middle face case, I see that it's -4/1. So I have a horizontal asymptote at -4. And so now you can really see what I tried to warn you about. There's going to be lots of things going on. But notice the similarities between these. Wherever I had a vertical asymptote on my purple function, that's where I have a horizontal asymptote on the red. And whenever I had a horizontal asymptote on my purple function, that's where I had a vertical asymptote on my red. Of course, they should be because they are inverses of each other. Okay, let's utilize the graphing calculator to do the rest of this work for us here. So in my first function, I'm going to put in the original 3 minus x divided by x plus 4. And then my inverse is 3 minus 4x over x plus 1. 3 minus 4x divided by x plus 1. Remember, you need to insert the parentheses. Otherwise, your graph is going to graph it incorrectly. At this time, I'm actually just going to turn on my original functions. We're only going to see the blue one here. I've deselected the equal signs. So that means these are stored in here, but they're not going to be graphed. So let me graph just the blue function. So we see this graph here, and we know that that makes sense because that makes sense with the horizontal asymptote, with the vertical asymptote, and with the horizontal asymptote that I found earlier. Okay, now let's go ahead and turn on the other two functions. So what my inverse looks like and the graph that it's going to be flipped over. So again, the red is my inverse function. And if I were to graph these, and if I were to flip these over that line of y equals x, they should match. And we can see that they do in fact match. Very difficult because there's lots of things going on, but we can see it's symmetrical on both sides of that line, y equals x. All right, so we've worked through a couple of examples of proving functions are one-to-one, finding their inverses, and double checking them by graphing them, either by calculator or by hand.